the force of gravity between two objects is equal to gm1 m2 over r squared. That force of gravity, that push or pull, I should say, because of gravity, depends upon having two masses. Here's the Earth. Here's my board marker. There is a force of gravity between my board marker and the Earth because there's two masses. But what if I take that board marker away? What if there's no longer anything there where the board marker was? It's now just empty space. There's not even air. Okay, let's say that we've sucked all the air out of the room. Nothing's there. There's literally not an atom of matter present right there where that board marker was. How do we describe gravity now? Well, we can't describe gravity as being a force because there's no pull on the board marker or anything else there. You need two masses, m1 times m2 over r squared. But the Earth hasn't disappeared. The thing that causes the curvature of space-time is still there. Gravity is still there, but we can't describe it as a force. So what we're going to do is create this way of describing it that we're going to call a gravitational field. In general, a field is a line of influence that surrounds something. A gravitational field is a line of influence that surrounds something with mass because it is a gravitational field. It shows us the influence of gravity, whether or not there is something there to be influenced. So again, we go back to the Earth and the board marker. Just because we take the board marker away doesn't mean that the potential influence of gravity is gone. It's just not influencing anything right now. You can say it like this. The gravitational field describes the potential force. If there's something there at somewhere down the road to experience that field, then there'll be a force. But if there's nothing there like the board marker to experience it, then all we have is this field, not a force, just a field, which is the potential to cause a force. Now, there's lots of types of fields out there. Gravitational fields, there's electric fields, magnetic fields, light fields, heat fields. Some of those fields are vector fields, and some of those fields are scalar fields. There's a direction associated with some fields. Gravitational field, clearly there's a direction. If I put the pen, the board marker, in the gravitational field, it will always experience a force downward, always. It's not a random direction. I don't stick the board marker in the gravitational field one time and have it go downwards, and then the next time it goes upwards, and then the next time it goes south, and the next time it goes north. It's not random at all. There is a specific direction associated with a gravitational field, so we're going to call it a vector field. The same thing would be true with an electric field or a magnetic field, as opposed to, say, a light field or a heat field. The light and the light bulbs overhead right now influence us. They influence us, but they don't influence us in a direction. So we'd say a light field is a scalar field. Heat field would be a scalar field. No direction associated with their influence. But gravity influences us in a particular direction, downwards, toward the producer, toward what caused the gravitational field. So here's the Earth, or any other object with mass, really, that generates a gravitational field. Of course, you can imagine the stronger or the bigger the mass of the object, the bigger the gravitational field that it produces. So let's use the Earth. It's pretty heavy. The gravitational field lines that surround the Earth would look something like this. This would be the shape of them. We call it a radial field because they kind of radiate out around the Earth. And those field lines, they have a direction associated with them because they're vector fields. They point toward the surface of the Earth. Now remember what we said. If you take an experiencer or something to feel that field and put it somewhere in that field, maybe put it right here. Here's a mass, here's a ball. If you drop it, where does it go? Downwards, towards the Earth. It goes this way. They experience a force in the direction of the field. What happens if I put the ball down here? Which way does it go? Downward toward the Earth. Why is that downward? because we define gravity, we define downward in terms of gravity. Okay, you ever think about this? People in Australia or Antarctica, like standing upside down on the Earth? Like they could think the same thing as us. Same thing as us, about us, right? Because in the end, we're on different sides of the Earth. But yet everybody's standing right side up with their feet down on the Earth. Gravity points downward toward the Earth. Gravity points downward toward the Earth in all cases. Well, one more thing that I want to point out to you about this diagram before we move on. This shows the direction of the field lines. It shows the effect on an object with mass. It shows what will happen if I put an object with mass there. Okay, if I take away these objects here, okay, there's still a gravitational field. There's still the potential influence of gravity. It's just not influencing anything right now. But it's still there. The curvature of space-time is still there. Notice how close or how far apart the field lines are. These field lines are pretty much the same distance apart. These field lines out here are further apart. What does that tell us about the field? The fact that some of them are close together, some of them are far apart. It tells us the strength of the field. The closer the field lines are together, the stronger the gravitational field is. Right here, it's going to be about, here's the question for you. Does anybody want to take a guess at what the strength of the gravitational field is at that point where I have circled by black circle? You might think, how am I possibly supposed to know that? Deep down, you do know that, actually. What do you think it might be? 9.81 meters per second squared. Okay. That's the gravitational field strength. It's the acceleration due to gravity. Look, if I take this board marker away, we would still say gravity is 9.81 there, right? That's the field strength, the acceleration due to gravity. That's what we've been talking about. What's it going to be up here? This is a weaker gravitational field. Well, we don't know what it's going to be up here, but we know that it's going to be less than 9.81 meters per second squared, right? It gets weaker the further you get away from the producer. That should make sense to us, right? The further you go up from the Earth, the weaker the gravitational acceleration, or as we now know what the gravitational field is going to be. Well, let's describe it with a couple equations. Okay, first one, not new. Okay, first one, gravitational force is G m1 m2 over r squared. This isn't really a field thing per se. It describes the force between two objects with mass, but it's related. The gravitational field can be equal to G m over r squared, or the gravitational field can be equal to F over m. This is what we call the producer equation. This is what we use when we have information about what caused the field. Okay, if we're looking at this last picture here, the Earth is what caused the field. Maybe a ball right here is what experiences the field, but the Earth caused it. If we know something about the Earth, then we use this equation. If we know something about the ball, or whatever it was that experienced the field, then we use this equation. We're going to call that our experiencer equation. Little g is the gravitational field strength. Big G is the constant, right? 6.67 times 10 to the minus 11. M, in this case, is a mass, right? Mass of what? The mass of the producer, the mass of the Earth in the diagram that we had on the previous page. as opposed to m down here, which would be also a mass, but mass of the experiencer. So the mass of the Earth in the middle equation, the mass of the ball in the bottom equation. R is the distance from the center of the producer. So if this is your diagram again, ball's up here, or even if there's nothing there, the distance from here, from the center of the Earth to wherever it is that you're trying to find the field, that's going to be R. And finally, F, the force experienced, the force felt. The force of gravity is the weight of the ball. Not mass, weight, m times g. Finally, what units do we use for gravitational field? Well, said that it can be meters per second squared, gravity. Take a look down here. Forces in newtons, masses in kilograms. So we can still call it, bless you, we can still call it meters per second squared if we want. But now we can also say newtons per kilogram if we want. 9.81 meters per second squared, 9.81 newtons per kilogram. Listen, if we already know the value, 9.81, why bother doing this? Why? Why bother doing it if the gravitational field is always 9.81? Because it's not always 9.81. What happens when you go to the top of Mount Everest? It's smaller because you're further from the center of the Earth. This is why it's smaller, because R is bigger. 9.7 something at the top of Mount Everest. Go to the space station, it's 9.0, 9.1, something like that. Go to higher up, it's smaller. What's the gravitational field on the moon? 1.6 meters per second squared. It's not always 9.81. Now we have a way of figuring out what the gravitational field strength is.